Going.
Hey.
How's Roku doing today?
Roku, I sold it. It had earnings like.
Well, if you want
The review is going to print over there, fellas, but you're not going to get staples, apparently.
Like 65.
Okay.
So like, it's at like 40 right now. Got the spot.
Yeah.
Has it started printing yet?
Yeah.
There it goes. Okay. Today, we are on Chapter 11, Part E. And the first thing that I'd like to show you is they never give you a picture of the basin that they're talking about. So I have the picture there on in the top here. In Preview 11E, you talk about water flowing into a basin at a constant rate, where the depth in inches is given by 12 square root t. In other words, y is measured in inches and t is measured in minutes. You can tell it's not going to climb inch-wise at the same rate. First of all, because it's a curved basin. Second of all, because the formula is not a linear formula. So what it's telling you is that as you get higher up, the rate is going to change. So the first thing we're going to do here is talk about this question. How might you go about calculating how fast the water is rising at 5 minutes? Well, till now, we've been doing average rate of change over a period of time, like, for instance, from 1 minute to 2 minutes. If you're driving down the highway and somebody asks you, well, how fast were you driving from 9:05 to 9:06, you would, if you had your cruise control on, it would be easy to say, right? But how fast were you driving at 9:05? There's a device in your car that helps you with that, right? It's called the speedometer. It tells you how fast you're going at that exact minute. But we've never calculated how fast is the water rising at 5 minutes. Well, that's what we're going to be doing in this lesson. Answer the following questions about the depth. Y of t equals 12 square root t. Page 170. We've got a bunch of different times here. Oops. Before we do number 2, let's figure out how deep is the water at 5 minutes. Using the formula y as a function of t is 12 square root t. What are we going to press? Say 12 square root 5. And then when I press that, I get the water depth is 26 .8328153 inches. Let's look at the graph of this function. So at 5 minutes here, oops, where's 5 minutes? At 5 minutes, the water depth is 26.833 inches. Page 170. Now they say they want to know for the time interval where you go T0 to T1, they want to know what is the average rate of change. Well, in order to calculate that, you need to know what y of t is at each of those times. Well, we already know y of t at 5 is 26.833. So for the interval 5 to 7, what other oops, you can't see that. So for the interval from 5 to 7, what other number do we need? Well, we need to know the 7, what the value at 7 minutes is, right? So let's see what that value is. So we'll press 12 square root 7. And does it make sense that the water is now 31 inches deep? Because it gets deeper all the time, right? So we'll write 31.7490153. Now I'm doing a lot of digits just because the very last people who are going to do the interval from 5 to 5.0001, that's a very small interval, so you need to have a lot of digits for that one. But for the first ones, you don't need to have very much information. Okay, finding the average rate of change. Obviously, we can't find the average rate of change if we only have one number. 5, 4, 3, 2, 1 on how good you are at finding average rate of change. Okay, in this case, let's do the denominator or the numerator first. Numerator is 31.749 minus 26.833 divided by 7 minus 5. So I'm going to have to use parentheses. 31.749 minus, 26.833, close parentheses, divided by 7 minus 5. Obviously, that I could have just done 2 there, right? And I get the average rate of change there is 2.458. So in other words, on this graph, as I zoom in between 5 and 7, the slope from here to here is 2.458. Let's do some, let's do some thinking. Does it make sense that it's sloping uphill? Yeah, because the water is getting deeper, right? Does it make sense that it's sloping up here slower than it was at the bottom of the dish? Yeah, because as you get higher up, it takes longer to fill a bigger portion of the dish. Okay? So, on this page, we have some pairs to do. We just did 5 to 7. Eric and Gavin, you do 5 to 6. Sam and Jake, you do 5 to 5.5. Nick and Lauren, you do 5 to 5.2. Marlena and Jess, you do 5 to 5.1. You two do 5 to 5.01. You two do 5 to 5.001. Menominee, you do 5 to 5.00001. And I'll give you a hint, Menominee. Use this value for 5 because you need tons of digits on yours because your values are going to be almost the exact same. Anybody not know what they're doing? So 5 to 5 or 5 to 6, did you guys get 2.56?
Yes.
5 to 5.5, did you guys get 2.62? 5 to 5.2, did you guys get 2.65? Now, if you notice, does it make sense that the slope is getting steeper the closer this point gets to 5? Right? Because you're getting closer and closer to the steep part of the graph. Where were we? 5 to 5.1, 2.67. 5 to 5.01, 2.68. 5 to 5.001, 2.683. And then a Menominee, did you guys get 2.683268157?
816. I mean, my
816. Hey, here's the deal. In other words, as you zoom in farther and farther here, I'm going to change my settings so that the X goes from 5 to, I'm going to say 4.99 to 5.001. And I'm going to change my Y to go from 26.8 to 26.85. I want to show that as I zoom in farther and farther, so here's my 0.5. Ooh, I didn't zoom in very far, did I? Here's my 0.5. And this 5.0001 is so close to it, it's almost the exact same point. Which leads me to ask, why can't I just find the slope at that point? Find the slope at 5. Just use the rate form to find the slope at 5.
The average rate of change is constant. The size of the basin changes.
That's true. But if I want to know the slope at 5, well, what would the math be for that? What would the math for the slope at 5? Oops. M equals f of 5 minus f of 5 divided by 5 minus 5. Would you agree the numerator will be 0 and the denominator will be 0? Now, the reason we can't do the math, or step 1, that does not mean the slope is 0. Right? Because think about what we know about fractions. If the numerator is the same as the denominator, the fraction is 1, right? If the numerator is 0, the fraction is 0, right? 0 divided by any number is 0. If the denominator is 0, we know we can't do the math. So the answer is either 0 or 1, or we can't do the math. Okay? All three of those are possible correct answers. Now, if we were going to give a good, well, and we know for a fact that the slope at 5 is not 0, it's not 1, and it's not, we can't figure it out because the slope at 5 is pretty dang close to whatever this, it looks almost like a line, right? We zoomed in so far, our curve looks like a line. And that slope of that line, according to the Menominee calculators, is, what'd you guys get? 2.5, 2.683?
Yep, 2.6832.
So, to find the instantaneous slope,
Hey, how are you? Yeah, all right. You're not excited? Yeah. So you got everything set for the speed working?
choose two values really close together. Okay? So the rest of you were kind of doing pointless math to find instantaneous slope because your points weren't really close together. Now, was there a big difference between, I can't remember, Laura, did you guys do the 0.00 one?
No.
You did the point, you did 1 0? So you guys did the 2 zeros. Was there a lot of difference between 2 zeros and 3 zeros? Not a lot. So choose two values that are really close together. Page 171. Now it says, let's analyze how fast the water level is rising at time 10. Well, the first thing that we probably want to do is to figure out how deep is the water at 10. So at 10 minutes, 12 square root 10. At 10 minutes, the water is 37.94733.192 inches deep. Does it make sense the water is deeper than it was at 5 minutes? When we do the slope calculation, now remember our graph, it's getting less steep, right? Would you expect the rate of change to be bigger or smaller than 2.83? Okay, you're filling water, right? And into that basin. and you look in, what's happening at the beginning? It's filling pretty fast, right? Then the farther you go along, what happens to the speed that it's filling up? It slows down. Does slowing down mean that it's draining out of the tank? No, it just means it's not filling as fast as it used to be filling. Okay? So here's our graph. And it's going like this, correct? We just calculated the slope at this point 5 to be 2.683. I can't remember. 2 point something. Now we want to see, this is the 0.5, right? Now we want to see, well, what is the slope going to be out here at 10? Okay? If we are going to do that, now in our book, they say choose a whole bunch of different values. But almost all of us did a useless piece of calculation, right? Because somebody else had a better answer than we did. So let's all do just one calculation on the instantaneous velocity. Besides the value y of 10, what would be a good value to find? $10.0001 is, and let's find out what that, did I have too many zeros? No, 3 zeros. Okay, so second function, square root, 12, second function, square root, 10.0001, and we get 37.94752166. If you notice here, my digits lined up for a long ways, right? If I would have just rounded to the nearest hundredth, they'd have been the same. The first time I'd have had a little bit of difference is if I'd rounded to the nearest thousand. Okay? So let's use that calculation to find the instantaneous rate of change. So our numerator is our second value, 37.9475216, minus our first value, 37.947333192, close parentheses, divided by parentheses 10.0001 minus 10, close parentheses, and we get a slope of 1.8974. Is that what everybody got? Now, on page 174, they show the math. Last test, a lot of people were still getting these questions wrong. How can you tell this is the average rate of change? Well, this is f of t1, 12 times the square root of t1. This is f of t0, 12 times the square root of 10. This is t2, and this is, or t1 and t0, I guess is what they call them. So make sure you get that average rate of change situation taken care of. Part D. we're going to change this average rate of change function from giving us the depth at 10 minutes to giving us the depth at 15 minutes. Write it down and see if the person sitting next to you has it correct. Change this formula to finding the depth after 15 minutes. So, if you wanted to find the slope at 15 minutes, what would be the other value you would plug in to your formula to give you the depth at or the rate of change at 15 minutes? $15.0001. Last problem. Now it says we aren't filling the basin. We're talking at a car. It's driving along a straight road. For the first 15 seconds, the function is f of t is 12t squared. We want to know how fast is it going at 9 seconds. Round to 3 decimal places. At 9 seconds. Okay, so I took 1.2 times, or I started a parentheses because I want to make sure I get the numerator right. 1.2 times 9.0001 squared minus 1.2 times 9 squared, close parentheses, divided by 9.0001 minus 9. Is that what everybody did? Is that the math you did? Did you get an answer? I haven't pressed equals yet. First of all, does it make sense that it is a positive number? Right? I mean, the car is speeding up, so does it make sense that the slope is a bigger number? Right? Everybody good? Did you get 21.60012? Instantaneous rate of change. I think there's a test question on it. Page 12.A, Introduction to Power Functions. In the preview, you investigate the drag force that a cyclist experiments while riding a bicycle. The drag force is a function of the velocity of the cyclist and is expressed as a power function. In other words, this number here is going to be a certain power. What are some reasonable values for the speed of a cyclist in miles per hour? Anybody a biker? 1? You are a slow biker. Okay. Anybody a little bit faster biker than that?
15.
15? Yeah, I can do, usually I ride about 12, 13 miles an hour, but I could do 15 if I wanted to. Would it surprise you if I said 100 miles an hour? Yeah, that would be kind of surprising. So it's probable that I would not be able to show you a bicyclist that's a video of a bicyclist that's going 100 miles an hour. So if I said there is a video of that, you would want to see it. So you have no speculation as to what would be occurring in order to have that happen. Well, have you ever gone faster than 15 miles an hour on a bicycle? How are you doing it?
Downhill.
Going downhill. Interestingly enough, I do have a video of a person going downhill on a bicycle. Let's see if we can find that picture. And show it to you. Where is it? College algebra. There we go. And lessons. And we're on 12A. Where is it? Oops. 12A. This might not have it. There it is. Oops. Come on. Here we go. Okay. Let's see, do we have any sound? And I'd like you to notice that it is such a steep hill. That guy is being chained to the steepness of the hill. See it? Or not chained, roped to the hill. So the guy holding him back. Look at that suit that he's got on. I've got to think they're a little worried about air resistance. Now, the helmet is superfluous anyway. That wind thing is good for cutting down, but the helmet doesn't do him any good. Notice he's not even pedaling. I don't even know if the bike has pedals or brakes. Now I think this was, I don't remember what they said. Oh, there we go, 228 kilometers per hour. Okay, so there's one circumstance under which you would be going faster than 100 miles an hour. Do you have any other ideas about how you would go faster than 100 miles an hour? Well, if you had no air resistance, I'll show you that one here.
Why wasn't there a ramp?
I'm sorry, what's that?
Why wasn't there a ramp at the end?
Yeah, I don't know. Next one. So this one I think is a little bit more interesting, a little bit more dangerous.
Hi, my name is Bobby Root, and I'm here on location where I'm going to attempt to break my world record that was set in the year 2000. Some of the conditions to beat this world record is going to acquire a flat road that is approximately 2.5 kilometers long in the draft of the vehicle while propelling yourself with your own human power. The tool that I have chose for this specific event
Did you see the bumper of the car there?
Carbon fiber. This thing is light, agile, aggressive,
So it's got the
stiff, and very
tailgate
fast.
open on a minivan. Once again, helmet useless. Now that's kilometers per hour.
So they got
My road bike speed record at 120 kilometers an hour was just beaten on a brand new Rose bicycle. I'd like to thank my sponsors for bringing me out here and my hairdressers for my great hair. I'd like to thank my teeth designers too, because I got the Tom Cruise teeth in for this event. I'm telling you, I'm the man for the job.
Okay, and then one more. I like this one the best because you got to watch his girlfriend. So he's just on a stationary bike, and the speedometer says he's going 35.
55, 60, 65, 70, 79, 100.
His girlfriend there.
148.
Okay, let's look at the math here in this problem. The math says that we're going to be talking about drag as a function of velocity is 0.383 velocity. Is it squared or is it cubed? Squared. Velocity squared. In other words, the faster you go, the more drag there is on the wind. Kind of makes sense, right? So, let's get some velocities here and some drag factors. So, they say 0. Well, the drag factor at 0 is 0. First table, what do you guys want to do for a speed?
We'll do 15.
15. Second table.
25.
Third table. Yeah, you too.
35.
Oh, no, I was talking to Lauren and Marlena. Sorry.
Just 30.
30. We need some other speeds besides getting faster and faster. Jess, what are you going to do? Now your table, Felicia.
5.
And Menominee, what are you guys going to do?
40.
Ooh, you are really cooking. Okay, these are speeds in miles per hour, so we're going to get these are velocities. We are going to get the drag factors. And then it says graph those values. Now, before I start filling in the graph, I need to get, the biggest number here is 40. So what did you guys get for a drag factor on 40? You know what you're doing? 0.383 times 40 squared. 612. So if we made this 600, okay, 40 miles an hour would have a dot right there. Okay, 15, what did you guys get? 86. 25, what'd you get?
239.
30 miles an hour, what'd you get?
345.
20 miles an hour, what'd you get? 5 miles an hour, what'd you get?
9.575.
And we have enough that we can fill in our table. So 20 is here, 10 is here, so 5 is here. And at 5, we're just barely off the graph, right? At 15, we're close to 100. At 20, we're close to 150. At 30, we're close to halfway, a little bit past halfway. Okay? So our graph looks like that. Is it linear? No. How can you tell? Well, the points don't line up. But according to the formula, it looks like it's going to be a quadratic, right? Because the shape is half a parabola. It's open up. Leading coefficient is positive. If we were going to graph it, we would have said up 1 over 0.383 both ways, right? You get the picture. So the question that they ask first is, number 3. If the person increases his or her speed by 0.1 miles per hour. So if you go 0.1 farther this way, 0.1 farther this way, 0.1 farther this way, 0.1, you always go 0.1 farther over. What is going to be true about the slope?
It's getting steeper.
So as the velocity increases, the rate of change increases. Part A. Are there any values for which the oh no, we're not there yet. We're up here. Then it says, let's consider another power function associated with the motion of the cyclist, and that is the mechanical power. In other words, we're going to figure out how much energy it takes to get a person to go a certain velocity. There are 2 factors that are making it harder as you go faster. One of them is you actually have to go faster, but the other one is you have more drag to overcome. So it shouldn't surprise you that the formula for m of v is 0.383v cubed. So, same ones, fill in your m of v's, and we're going to graph that. I'm just going to have to change this total right here to a different number for that graph. Well, m of 0 is going to be 0. That'll be easy. We need to get the 40 so that we can tell what our top of our graph is. What'd you get?
6.128. That doesn't seem
6.128, really?
right. I did 4 and not 40.
Oh, yeah, you did 4 and not 40. Yeah, so it's 0.383 times 40 to the third is 24,512. So if we made this 25,000, that'll be a good spot for our graph. Okay? Other people. So this is 24,512. What'd you guys get? 15.
1,292.65.
25.
5,984.
30.
10,341.
20.
10,064.
5.
47.
What do these numbers mean? Well, it gives us, it tells us its power, but it doesn't give us the dimension for that. That's in watts. So 47 watts. If you're bicycling, you're putting out about as much energy as a light bulb. If you are going 15 miles an hour, you're putting out over a kilowatt. A horsepower is 746 watts. So you are generating more than a horsepower if you are going 15 miles an hour. If you're going 20 miles an hour, you're generating 3,000 horsepower. I'm sorry, 3,000 watts, 3 kilowatts, which would be almost 5 horsepower. Okay? And then you've got 10 kilowatts and then 25 kilowatts. Well, we know that the bicyclists in the Tour de France can go really fast. Something about this equation does not make sense for those bicyclists in the Tour de France. What is it?
Their drag is minimized.
Very good. That drag constant that we multiplied by, which was 0.383, is going to be smaller. Is going to be a lot smaller. How do they get it smaller, Jake?
They draft each other and they wear a different type of material.
And they ride their bikes differently than ordinary people do too, right? They are much more slouched over than you are when you ride your bike. Okay? So they cut down on that wind resistance, which makes it so that their 0.383 is probably a lot smaller. I don't know what their drag coefficient is. We could look it up. Oh, let's see here. Bike racer drag coefficient. Let's see. Yeah, I don't see, let's say, Tour de France. Let's see if they give us a drag coefficient there. Oh, they got the C, but they don't tell us what the C is, do they? Be nice if they did. Anyway, it's probably a lot smaller than 0.383. Page. Oops. Number 5. Now, if a cyclist increases his or her speed by 0.1, how much does the mechanical power change? So now we're going to go 0.1 this way, 0.1 this way, 0.1 this way, 0.1 this way. Oh, we didn't ever put these points in. We better do that first. So at 5, we are at 47. At so that's a little bit lower, isn't it? If that's 25,000, this is 12,500, and this is 6,250. Okay, so at 25 miles an hour, we're still down here, right? At 30 miles an hour, we're up to 10,000, and at 40 miles an hour, we're there. So what do you see is true about our values? Well, our values are bigger, but not bigger compared to the way that they were before. I've got it graphed here in Desmos to show you that we've got a cyclist. Oops. Didn't I do the... Here we go. So here is, if we are at, let's go from 0 up to 20 miles an hour. And let's go in the y direction from 0 up to 3,000. Okay, so you can see that the green line here, the power, the mechanical power function, is much bigger than the drag function is, right? The question that and then they said, for each 0.1 mile per hour or meter per second increase, for each 0.1 meter per second increase, what's happening? Well, as velocity increases, the rate of change also increases, correct? And it looks like it's increasing much faster than the other one did. Bottom of the page. If we had f of x, which is x squared, and we compared it to g of x, which is x cubed, are there any numbers for which g of x is greater than f of x? Where if you square a number and you cube a number, the cube is going to be bigger.
Is it every number that's over 1?
Every number. Sam looked at me like, dude, I think all of them do, right? But now you modified it and you said every number greater than 1. The cube will be bigger. Okay? Why did you say bigger than 1?
Because if it's 1, then the answer is 1 for both.
That's true, right? 1 cubed is 1. 1 squared is 1. It's 1 for both of them. You're right. We'll take our break. When we come back, we're going to do another kind of power function, 12b.
Was the water cleaned up yesterday already?
I can't be in there. The sound of the of the fans is just way too loud.
Yeah.
Is it actually good? Like a good beat? I know. Which is but it's just weird there. Yeah. It's kind of like the You're in Tibet. I have to go to my exhibit.
Did you go?
I don't need it.
Smaller. Most of the size of my head. I was like 5. Totally entranced me. So it's 3 times my hair. 5.
All right. Page. I don't know what page this is on. The the beam that is broken. We're still on power functions. You calculated the stress in a structural support column with the cross-sectional areas. Such columns can fail by collapsing upon themselves, as shown in the photo. Now, usually when they collapse, it's not because the pressure goes straight down. There was probably some kind of twisting that caused it to get off center. What do you think caused this one to fail? Maybe rust in those beams up there. Maybe an earthquake. I don't know. Something caused it to fail. Let's look at the formula. I gotta get the formula up here. So the formula says the stress, that's the Greek letter sigma, lowercase sigma. Stress here's how you make that Greek letter sigma. It's lowercase sigma, by the way. Uppercase sigma looks like that. Stress as a function of area is 150,000 divided by the area. Now, it said this is a power function. Well, I don't see any special power here, do you? A in the denominator is the same as a to the negative 1. So it is a power function. It's an inverse power. The following graph, it says, shows the relationship between stress and area for a beam. Now, you can tell this is an inverse graph, right? Because it gets really, really, really close to 0. We remember that. So the smaller the column is, the more stress it will be under. The bigger the column is, the less stress it will be under. You can never have a column that has no cross-sectional area, and you can never have a column that has no stress. It's not going to cross either of those two lines. So then they show the areas for each of the different sizes and the amount of stress that they're under, which kind of makes sense. Let's look at the next question. Number 3. How does the stress change as A increases? As area, increases, stress, which direction is stress going? Decreases. As area increases, stress decreases. Do you think the value of the stress ever reaches 0? No matter how big you make that beam, it's still going to have some stress on it. Okay? Now, the next page doesn't show the amount of stress. It shows what's happening to the rate of change. So here's the rate of change. 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 So as the area increases, the rate of change, well, which Would you agree the rate of change is always negative? But it's getting closer to zero, right? It's getting closer to zero. So let's look at this first calculation that they gave us. 300 to 400. So our denominator is 400 minus 300. Our numerator is the stress at 400, which they told us was 375, minus the stress at 300, which was 500. So on my calculator, the average rate of change for the interval from 300 to 400 was, parentheses, 375 minus 500 divided by, parentheses, 400 minus 300, which doesn't surprise us that it's a negative number, and it is negative 1.25. Menominee, you're doing 200 to 300. Back table, you're doing 700 to 800.
Is that us?
That's you guys, yep, Felicia. 1400 to 1600. Ladies, that's you three. 2500 to 3000. Fellas in the front there. 4500 to 5000. Front left table, or right table for you guys. Anybody have any answers to report?
Yeah, for 200 to 300 it was 2,500.
Nope, that's not right. What was the math that you did on your calculator?
Took 750,000 minus 500,000 over 300.
Just right. But the stress was for 200 to 300. The stress at 200 was 750. 300 it was 500.
Oh, I thought those were in thousands.
No, it says pounds per square inch.
Is it 5?
No. So if you take parentheses, yeah, it could be. Yes, it could be negative 5, right? Except for I don't think it is though, because if you take,
it's 2.5.
yeah, negative 2.5, right?
Yeah.
Negative 2.5. Ladies, what'd you get?
Negative 2.68.
What'd you get, Jess?
I don't think I'm doing this.
So for yours, you would take 800, which is parentheses 187.5 minus 700, which is 214.3, close parentheses, divided by parentheses 800 minus 700, close parentheses, and you get negative 0.268. Oh, did I do the wrong one? I should have been doing 1400 to 1600. Sorry about that.
Yeah, I get what I did wrong. I mixed up the bottom.
So what did you guys get, Lauren?
Well, I got negative 0.665.
2500 to 3000.
Negative 0.02.
And 4500 to 5000.
Negative 0.0066.
Okay. So you can see as we get farther and farther along that this stress keeps getting closer and closer to zero.
It's just rate of change.
But if you
It's like it's negative.
But if you notice, these up here, we were doing the rate of change when we went like over 100. It was like this. Over 100, it was like this. Here we went over 200, and the reason we had to go over 200 is that our up was so close to nothing. Here we went over 5,000 just to get it so that we would see a little bit of decrease. Here we went, or not 5,000, 500. Same thing here. We had to go 500 just to get any kind of an increase that was measurable. Page. Oops. So write a sentence that describes how the rate of change on the function changes as the stress increases. Well, what happens as the stress increases, the rate of change decreases and gets closer and closer and closer to zero. Or is that increasing? Yeah, that's increasing, isn't it? These numbers are increasing. Correct? Negative 0.268 is smaller than negative 0.0665. They're increasing as they get closer and closer to zero. All right. If a column is under too much stress, it will fail. The amount of stress that causes a column to fail is called the failure stress. So if we look at our column and we say it's going to fail at 150 pounds per square inch, 150 pounds per square inch, how big is the column going to be? If it fails at 150 pounds per square inch. 1,000 square inches. Everybody see that? It's going to fail at 1,000 square inches. So we have to make it bigger than 1,000 square inches. Then it says, if the failure stress of such a column is 200 pounds per square inch, what size column do we need? 200 pounds per square inch. What size column do we need? Close to 700 square inches, right? To get to 200 pounds of failure, or failure at 200 pounds. Okay, so we have two columns, A and B. We have two columns, A and B. A, it says, is presently under 300 pounds per square inch. We want to make it bigger so that it will be able to hold 350 pounds per square inch. Column B, it says, is presently holding 125 pounds per square inch. We want to make it bigger so that it will be able to hold 50 pounds more than that. 175. Okay? So in both cases, we are increasing the amount of stress they're under by the same amount, right? We're going to increase the stress here by 50. Remember, stress is our vertical axis. So we've got 50 there. Oops, I should have used, oh well, I'll change colors. This one is also going to be 50 pounds different in the stress direction. The question is, what's going to be true about the amount of area we're going to increase in each one of those cases? Okay, so on your chart, start at 300. Well, actually, why don't you use the formula? The formula says stress as a function of area is 150,000 divided by the area. Well, if you take 300, that's how much stress it's under. How much area would it have? 150,000 divided by 300 pounds will give you 500 square inches of area. Does that match what the chart says? 500 is 300, right? Now it says make the stress 350 instead of 300. What's the area become? $429, right? So if you increase 50 pounds of stress, you increase the area. What is that? 70 minus 350 is 78. So that change of 50 pounds results in a change in area of 78. Over here, a change of 50 pounds. Well, the stress, to find the area here, we'll take 150,000 divided by 125, and we get area is 1,200. Now we want to increase it to 125, so 150,000 divided by 175 is 857 minus 1,200. So in this case, we have to go over 342. So you can see that this beam that was under 300 pounds of stress only needed 78 more square inches to take on another 50 pounds. Whereas the other one, the stress was much, much lower, meaning the area was much, much bigger. And so to reduce that stress by 50 pounds took another 342 inches of area. What they're trying to show you is that when you engineer a project, to decrease a parameter, sometimes it's almost impossible to do. And this would be one of those cases. You can't make it so that that beam has virtually no stress on it, because you couldn't put enough concrete into your beam in order that it would be able to hold all of that weight. One more on power functions, and that is the illuminance problem on page 181. One of the things that I've noticed about streetlights is, and I don't know if you guys have noticed it too, but the streetlights in Eau Claire, they're really getting so that they save just tons of energy. We got a new streetlight out in front of our house. I'll show you the picture. Oops. So you can see how the street light there. Would it help if I turned it sideways? It doesn't get much bigger, but you can see how the street light is able to shine down, and you can see the brightness of it. One of the things that I'd like you to notice about it is, as you get farther and farther away from straight underneath the street light, the light gets dimmer. They show you that in our problem in our book. It says the illuminance is the brightness divided by 12 times the distance from the light source, the square of the distance from the light source. In other words, this is just like the function that we had up here on this page, except we're going to have not -1, but -2 is our power, 12.57. And it's going to be under phi, is that? Yeah. Under phi. Page 182 says the brightness of a light source is 950. Is the function E is a power function. Coefficient is -2, right? So this is R is to the -2nd. The table and the graph showing the relationship between distance and power is shown on the next page. So let's look at that table. And it looks an awful lot like our, like the one that we just did. Notice it's got it doesn't ever cross the zero line. Of course, it won't ever get infinite or brighter than, closer than 0. And as you get farther away, the brightness gets dimmer and dimmer. Let's fill in the table. These are rates of change of illuminance. So let's look at the math for that first one. It says if we go from 0.125 back down to 0.1, the illuminance changes from 4,838 down to 7,560. So our math looks like this. And when we press it on our calculator, 4838 minus 7560 divided by parentheses 0.125 minus 0.1, close parentheses. You notice that the illuminance is what they said it was, negative, it's going down, negative 108,880. Page 182, let's fill in the illuminances that are missing. Nick and Jake, do the first one there. Marlena, you guys do the second one, this one right here. Felicia, you guys do this third one here. Menominee, you guys do this one. And Eric, you guys do this last one. So you're doing the rate of change in illuminance. .150, what'd you get? Or 0.250, or anybody.
For the last one, I think it's negative.
Anybody else?
Yeah, I got negative 250.
I got negative 360. Because negative 250 is the one that's given there.
Oh. Whoops.
You have to take this number minus this number divided by this number minus this number. Anybody else?
Negative 59,120.
Which one was that for?
The 0.15.
Negative 11,320.
Is that a better number for you, Menominee?
Yeah.
Okay. And then I don't know who are we missing here?
We got negative 1,420.
Okay. So you can see as we go farther and farther forward, our slope gets closer and closer to zero. It's always negative, right? So it gets bigger, negative, gets bigger all the way, or closer and closer to zero. What are the units for the average rate of illuminance? You know what? We haven't done a lot of reminding ourselves what the units for rate of change are. Remember, it's always this axis over this axis. So we would say lux per meter, right? It's this axis over this axis. Slope is the change in y over the change in x. So in this case, the rate of change is in lux per meter. So use complete sentences to describe the average rate of change of illuminance as the distance increases. As the distance increases, the average rate of change is always negative, but gets closer to 0. It's always negative, gets closer to 0. Next. Estimate the distance that an object would have to be moved to reduce its illuminance from 5,400 to 3,000 lux. How far would you have to go from 5,400? Well, that's not on the table. 3,000 is not on the table. So we have to use our math. Use our math to figure that out. E of 5,400 and E of... No, that's not distances. Those are our E's. So we want E of some R to be equal to 5,400. And we want E of some other R to be equal to 3,000. In our formula, it tells us that E is phi over 12.57 12.57 R squared. So we will take 5,400 is, I forgot what it said our illuminance is. 950. $5,400 is 950 over 12.57 R squared, and 3,000 is 950 over 12.57 R squared. Find those two R's. Go.
Where'd you get the 950?
Page. I'll show you. What is the brightness if the light source is 950 lumens?
All right.
You could also estimate it from the graph here. If you notice, 5,400 is about right here, and 3,000 is about right here. So it looks like you're moving it. Distance is that about point. That's not very far, is it? 0.06 meters, something like that. Let's do the math. So to get R squared all alone in this first one, multiply both sides by R squared, and we would get R squared, and then divide both sides by 5,400. R squared is 950 over 12.57 times 5,400. So 950 divided by parentheses, 12.57 times 5,400. And then we have to, that's what the square is, so we have to square root that. So second function square root of our answer is R is 0.118, which is about what we said. Do the same thing for the other one. R squared equals 950 over 12.57 times 3,000. So 950 divided by parentheses 12.57 times 3,000. And we want to get the square root of that, so second function square root, second function answer. And we get 0.158. So it looks like we move it about 4 centimeters to increase the light source by that amount.
Kevin,
Yeah.
that was a little quick for me. What was our first step to figure all that out?
Okay, so up here, I have 950 over 12.57 times r squared is 5,400. I can't have r squared in the denominator. Now, it strikes me that one of the things I could have done is I could have written this as r to the negative 2, and then it would have been on top. But that wouldn't have helped me because eventually I'd have had to put it on the bottom anyway. So what I did first is I multiplied both sides by r squared. So if I multiplied this side over here by r squared, the r squared will cancel. But then I had 5,400 r squared. So instead of saying 5,400 r squared, I took 950 divided by 12.57 and just moved the 5,400 to the bottom of that other side. So basically what I ended up doing is I switched the position of the r squared and the 5,400.
Okay. And that 950 divided by 12.
And I did the same thing here. Switched the position of the r squared and the 3,000.
Okay.
All right. The reviews are on your printer up there, you guys, in Menominee.
We have it.
You have them?
Yep.
Let's take out our reviews and let's get them done. Jesse, you can either work by yourself if you want to, or you can work with one of the other groups. Don't care. The answers are on the back. Test is on Monday, first thing. It is. It is open book. Make sure you remind me of that.
I'll just take notes.
Let's get it done.
Book doesn't have any answers.
We do, but I'll be sure to know.
Okay. Did you already use it? It's actually
I did it like 3 times. Yeah.
It was great. Probably won't appear in your thing for very, very soon though. Did you guys need some help over there, Menominee? Or are you okay?
we're all good.
We're good.
So you aren't going to work on it during class, is what you're telling me?
No, I'm going home to take a nap. Yeah.
Luckily, I don't do that during class, huh?
If you want to, that's fine. You feel free to do whatever you need.
It's 1 to 3.
So Eric was the only one that wasn't in Menominee today, Michael?
I was so close. Eric wasn't around.
Or was he there?
Eric was here, just Michael wasn't here.
Oh, Michael wasn't here. Okay.
I did it so many times where I just couldn't move.
Bless you.
Thank you.
How did you get this number? 10. Oh, like 60. Yeah, I was bad. But you're saying 100. Yeah, because.
So
Practice and then see. We'll see.
Alright, so you know that plan so this is going to be
right, which is like
I asked literally. A self-filling construction.
Oh my god,
This one's gonna take me 3 hours.
it's just gonna go through the whole alphabet.
You just guess it.
okay. So then what?
You're close, but you're wrong. Yeah. Okay.
Kevin, is the test multiple choice or short answer?
It's multiple choice.
Will it ever be short answer?
That one won't, because it's already multiple choice.
No, yeah.
Do you mean will another test be short answer?
Yeah.
I don't think I've got any short answer. I've got them all so that they can be that group test scratch off thing.
So I have a question.
Which number? Plan A costs 100. Plan B costs, oh, you have 125, and it's 128.
I don't understand. Oh, it's understanding.
And then 180. Oh, no. I just wait. Plan B, the customer sends the cost is 133. So where's Plan B without? Plan B is 125. Plan A is 100. So your 2 points are 100. 100 is 0, right? So 0 costs you $100, and 180 costs you 128. Right? So that's the first one. The second one is
So that's what's across.
125 is 0, and 133 is 30, which is a lot more. Well,
Because what I did was I divided the number of messages.
oh, okay. Well, that'll work too. So well, that's because this one is way wrong. Yeah, because each message is not going to cost you $6. That's a good question. That's why I'm asking you. Each extra message. So it's you had 180. Or I'm sorry. Yeah, 180 extra messages. But it costs you $28 for what? Yeah, $28 more. Okay, then do the other one. This is $8, 330 messages divided by $8. Oh, we're doing it the wrong way. It's the change in Y. So Y is $28 divided by 180 messages. And then the other one is $8 divided by 330 messages.
You know what each text costs.
Well, what kind of okay, so what the only thing I did was
Right. And this one costs like.
Why does your calculator have red and blue both? Patriotic?
I don't know.
So
You probably lost this and then you took somebody else's calculator cover.
My cover is just green, so I don't have
I feel like
so you're right there. Because
That would be so kind of like when you were a kid and one person wear a red sock and the other one would wear.
so it's not, you're off by like $1. One cost you $49.60.
We have a last test.
There's not like an actual final.
There is not a final test. But the last unit is kind of long.
Oh, okay. My bio class does, but just I'm gonna see if I can get out of it. Yeah, we'll see if I can take it.
I guess you.
So this is
Yeah. I am so sorry. I'm only here till the end of this. I'll write too much. On the bright side, you get more. I'm driving 45.
Oh, this should.
Okay, so what happened to your 290?
Yeah, sometimes.
299. That's how I got my name.
All my
You should have just said these.
Oh, okay, you guys go together. And what did it say to you? Yeah, well, minus 1/4 is pretty close to 23. Maybe your math was.
Like the same answer for 9 seconds.
Yeah, and all I'm saying is that 1/4 is pretty close to 23 divided by 92. That's really close.
Yeah.
So, in fact, this 23 divided by 92 this one. So all they did was they split it up into two separate fractions. You just kept it with the same denominator. You saved things. Because you only wrote the denominator one time. They wrote it twice.
Would I still get that wrong then on the test?
Number one, it's multiple choice. Number two, both of those won't appear.
Honestly, I'd rather get all.
Number three, if it was,
I would give you credit.
E36, I mean, my math class, they have no compassion. Zero compassion.
No, we had 5 weeks.
We come back with 3 words.
Minus every point.
We go back
What the blood going?
It's louder and it's not down there right now, so I'm going to find a different place to work next period. There's probably 20 fans going.
Yeah,
They're going to have to, super clean the carpets. Because any organism that had fallen to the ground over the last 5 years since that carpet was installed now has water that it can live on. And so it will spring to life and grow and multiply and die and give up a stink of epic proportions.
So it's been 5 years since the last.
No, since they put a new carpet.
Okay. I was gonna say how I didn't know how often it floods down there.
When did it flood last? That's a good question. Maybe 10 years.
Oh, okay. Well,
I have not always had an office in the basement when it's flooded, so it's difficult to know how often it's flooded.
okay.
I'm on my 7th or 8th office, although I've been here for quite a while. A few years. 4 years.
Shuffle your
So, I'm almost like I'm interested in place.
Oh, yeah, the one that we were working on in class.
Yeah.
Are you guys coming in here?
Copy like the last few ones up, yeah. No problem. Yeah.
That's your...
Go right to see.
Supposed to be doing it, but I don't know where they are. Yeah, I know, but I don't know where.